Hello, this is a presentation on welding fundamentals. In this presentation, we'll discuss how to place a weld, the different processes that are used, the different weld positions, the different electrode types, and things of that nature. If you're looking for a discussion about the strength of welds and how to design them and calculate their capacity, that's covered in a separate presentation. Let's get started. When we look for guidance for welding and welded connections and joints, one of the first places you would look would be in the AISC Manual, Chapter 8, which is titled Design Considerations for Welds. There's a lot of good information there, and then you can also look at AISC Specification, Chapter J. Section J2 covers welds and welded joints specifically. However, if you're really going to become an expert in welding, or if you're really going to look up details associated with welding, you want to look at the American Welding Society specifications. And there are a number of them. This slide shows D1 through D1.1 through D1.9, and each one of those covers different aspects of welding. D1.1, the structural welding code for steel, and D1.5, the bridge welding code, are the two that are most applicable to what a structural engineer would encounter. Excuse me, I'm citing the 2010 edition of both of those specifications here, but there might very well be more recent editions available. I haven't updated this slideshow with respect to the AWS specifications in a bit. So in this slideshow, what we're going to do is cover first the governing specifications. I'll focus mostly on the AWS D1.1 specification, talk about joint types, welding processes, electrodes, weld sizes, backing bars, weld symbols, and then we'll conclude with a discussion of welder and weld operator qualifications. So this is AWS D1.1. This is an older edition of it. It's the 2000 edition. It's actually the one, though, that this slideshow is based on. I know that there are newer editions, but I just haven't taken the time to update this presentation for those newer editions in a while. Still, even if the letter of the law has changed a bit, the concepts are still roughly the same. So section 1 of D1.1 covers general requirements. It's the basic information and the scope of limitations of the code. Section 2 covers the design of welded connections, requirements for the design of welded connections composed of tubular and non-tubular members. Section 3 covers pre-qualification of weld procedure specifications, and Section 4 covers qualifications. Section 5 deals with fabrication. Section 6 addresses inspection. Section 7 covers stud welding, and Section 8 covers strengthening and repairs to existing structures. AWS D1.1 Section 1.1.1 gives us limitations or the scope for the specification. In fact, it says that the code is not intended to be used for steels that have a yield strength greater than 100 KSI, steels that are thinner than 1/8 of an inch, pressure vessels or pressure piping, or base metals other than carbon or low alloy steels. Okay, section 1.3 covers the mandatory provisions, and there are two different annexes or sections, two different types of annexes or sections. One that is denoted with Roman numerals that are mandatory, and others that are denoted with letters that are non-mandatory. And those are similar to what the commentary would be like in the AISC specification. Okay, here's a list of the mandatory annexes. So 1 through 7 on the left, 8 through 12 on the right. So we deal with the effective throat of welds, the effective throat of fillet welds, and skewed joints, etc., etc., etc. And on this slide is a list of the non-mandatory annexes. So short-circuiting transfer is a method of depositing weld metal. Sample welding forms, contents of weld procedure specifications, etc. Okay, section 1.4 covers definitions. AWS D1.1 section 1.5 covers weld symbols. Section 1.6 covers safety precautions. So At this point, let's go ahead and start talking a little bit about the nuts and bolts of welding. Good pun there, right? And so here are the 5 different types of joints that we would see in welded connections or welded joints. You can, in each case, we're basically taking 2 plates and we're welding them together. And the type of joint that we're looking at is defined based on how the 2 plates are being joined. So if you butt them together side to side, you end up with a butt joint. If you arrange them in a T configuration, it's called a T joint. You could have a corner joint, as is shown in the upper right. You could have an edge joint, so the weld would be placed along the edge of this joint, like right along in here. Or in this case, here is a lap joint where you would place probably a fillet weld in that region right there. So we have 5 different types of joints: a T, a butt, corner, lap, and edge joints. So depending on how you categorize it, there are basically 2 or 3 general types of welds that could be placed. There's a groove weld where you actually fill a groove with weld metal, or there's a fillet weld, or you could look at a plug and a slot weld. And on this slide are 10 examples of different types of groove welds. So the light gray material here would be base metal, 2 plates that are being joined. In each of the cases, this would be a butt joint. And the black represents the weld metal that's placed. So in the upper left, you can see a square groove weld. Just below that is a single V groove weld. If we go one more down, we see a double V groove weld. And so you can get the gist of this, that in each case, we're basically using terminology to describe the type of groove that is being formed in the base metal and then filled with weld metal. So in each one of these cases, if these 2 plates were being joined, you would have some type of a weld prep where you actually come in and grind the edge of the plate to form the groove, or they make special equipment that actually cuts at an angle like that to give you the groove weld. And then you would position the plates relative to each other and then use a welding process to place weld metal in the groove and join the weld metal to the base metal. So at the lower right, you can see a flare bevel type of groove weld, and that's a special case where you have a rounded edge joined with a flat edge, or in some cases a rounded edge joined with another rounded edge. And here's examples of flare groove welds. You have a flare bevel shown on the left. In this case, the example is an HSS member welded to some sort of a flat plate. And in the example on the previous slide, we had a round bar welded to a flat bar. On the right, on this slide, you can see a flare V weld, and that's 2 HSSs that are welded together, and the groove that forms and is subsequently filled with weld metal looks more like a V than it does a bevel, so they call it a flare V. Most of the time we can get away with specifying fillet welds, however. Fillet welds are easier to make, they're cheaper to make, and they can often accomplish what we need to get done. And this is a profile of a fillet weld. So you have the base metal, the lighter gray on the outside. You have the weld nugget, which is primarily the weld metal, the material that's deposited from the electrode during the welding process. But there's also a heat affected zone, an HAZ, and that's the material that's part of the base material that mixes with the weld metal and gets hot enough that it exceeds the transition temperature of the base metal. And you probably recall that when you exceed the transition temperature, you change the grain structure of the steel and you affect the mechanical properties. So things mechanical properties that are associated with heat affected zone are reduced ductility, maybe change in the yield strength or the tensile strength of the material, etc. So some other terms here, you have the weld nugget, the root of the weld, which is down in this region here. You have the face of the weld, and you can see this would be the throat of the weld. And I think I have that defined on another slide, and it's certainly defined in the presentation on welded connection fundamentals, where we talk about the strength of where we talk about the design strength of welds as opposed to welding processes. Excuse me. So then the last type of weld that you'll see is a plug or a slot weld, and this is basically made when you drill a hole or make a slot in one member, overlap it on top of another, and then fill that plug or fill that hole or that slot with weld metal. Now these aren't that great. They don't have a high strength level. They're not as reliable as some other welds. So typically you use them only for shear and in certain limited conditions. This is an example of a beam to column connection. So you can see that there is a shear tab coming in from the column here. This is a column flange in this region here. And what you can see is a beam flange down here. And this has been prepped so that you can have a single bevel groove weld placed between the bottom flange of the beam and the flange of the column. So what they would do is come in and put a backing bar in here to close that gap, and then place weld metal in there to join the bottom flange of the beam to the flange of the column. This opening right here is called a weld access hole, and that's to allow the welder to actually stick an electrode through so he can weld continuously from the far edge of the beam flange all the way over to the near edge of the beam flange without stopping in the middle. You can also see here these were twist-off bolts or tension control bolts, and when they tightened them, the splines that were on the end of the bolts fell down and are deposited on the flange of the beam. Okay, here's a couple other examples of weld preps. So this is a beam shown here on the right where you have a single bevel prep. This bevel has a steeper angle, looks like a 45-degree angle. Here is the weld access hole for the bottom flange and the weld access hole for the top flange. And then this is a similar beam on the left where the beam has been bolted into place. This is a backing bar here on the bottom and a runoff tab shown here, and we'll discuss those later on during the presentation, but basically they're in place to contain the weld metal and to allow the welder to weld continuously off the edge of the beam flange so that they can have a high quality weld even near the edge of the beam flange. Okay, let's shift gears a little bit now and talk about different welding processes. They all have one thing in common. They basically use an electric current to generate heat that melts part of the base metal, or the parent metal as it's called out in this sketch, and the electrode core. And the idea is that those two molten metals mix together, and when they solidify they form one continuous cohesive joint between the two pieces of parent metal. So basically every electrode has some sort of flux associated with it, and the idea is that flux provides a gaseous shield so that impurities from the atmosphere don't enter the weld metal while it's molten. So if you're not careful, if you don't have proper fluxing agents, then you can get nitrogen impregnating the weld, and that could lead to an inferior quality weld. It could lead to some type of a failure. So on the right is shown a weld machine, and basically it serves a couple of different purposes. All of them will generate some type of an electric current so that you can use that current to melt the weld metal and part of the base metal. And the one that's shown here looks like it also feeds the welding wire through the through this gun right here. And also, because there's a regulator here, suggests to me that this is a weld machine that uses gas as a fluxing agent as opposed to a solid flux coating. So when we look at the type of electric current that's used, you can use either AC current, alternating current, or you can use direct current, DC. And you get different welding characteristics out of the two options. When AC current is used, you get a base metal cleaning action that actually cleans on the alternating phase of the current. So this is good if you find that the base metal wasn't properly cleaned. If you use an AC type of welding current, then that gives you a little bit better results. If your weld machine is set up in a direct current configuration, then the flow of the electrons goes from negative to positive in a straight polarity arrangement. When DC negative is used, then the molten droplets flow to the base metal from the electrode, causing a very fast deposition rate of the weld metal. If you talk to a welder, they might refer to this as fast freeze between the electrode and the base metal, because the base metal is cooler while the welding is going on, and thus it's a good choice for sheet welding or welding pieces that don't fit up particularly well. If you have a DC positive arrangement, then the electrons flow the other way. They flow from the base metal to the electrode, and you get more heat buildup in the base metal. This allows for a bigger weld puddle or weld puddle to form, and it transfers the molten droplets a little bit more slowly than using DC negative or AC current. So here are 4 of the processes that are used quite often. You have shielded metal arc welding, SMAW, flux core arc welding, gas metal arc welding, or submerged arc welding. We'll talk about each of these in the subsequent slides. So shielded metal arc welding is probably what most of you think of when somebody says you're going to weld 2 pieces together. It's basically you use a stick electrode with some type of a gun, and you have a clamp going on to the workpiece so that you're actually transferring current through the grip that's shown here down through the electrode into the base metal, forming the arc that melts the electrode and the base metal. So if we look at a sketch, the core of the electrode is metal, some type of a steel, and it's coated in an outer, it looks like a cake. It's a flux coating. And when the electrode melts away, that outer flux actually forms a gas, and that gaseous shield protects the molten weld puddle from impurities in the atmosphere. After the weld puddle starts to solidify, you end up with a slag on there, and oftentimes you'll see a welder going through with a hammer and chipping away that slag. So here's the clamp over here on the right, the electrode inserted into that clamp, and then you can see the negative clamp over here on the left. This piece here would be clamped to the workpiece, and this would be brought into contact with the workpiece here, and then arc would be struck, and then the weld metal would be deposited. So this is one of the simpler forms of welding. One of the shortcomings of this, however, is that when the welder is actually placing the weld, the electrode changes length during the welding process, which makes it a little bit more challenging, and you actually have to stop welding every so often and reach for a new welding rod. And if you're placing a long weld, that could be tedious. Okay, another form of welding is called flux core arc welding, and in this case you have your electrode as a wire, and it has the fluxing agent at the core of the wire. So the wire is actually hollow, it's filled with the fluxing agent, and the welder here has more or less a gun in his hand, and by depressing this trigger he can control the feed rate of the wire. So he can control it to feed either slowly or fast, depending on how fast he's moving along placing the weld, and depending on how much heat is present, etc., etc. So this slide depicts gas metal arc welding, and it's similar to flux core arc welding in that the electrode is a wire and it's fed through a gun. But the difference is that this wire would be solid, and the fluxing agent would be a gas that is blown out around the electrode. So the typical gases that are used are helium, argon, or carbon dioxide. And one of the shortcomings of gas metal arc welding is that if it's a windy day, then the wind can blow away the gas, and it doesn't do an effective job of protecting the molten weld puddle from the impurities. So that's one of the limitations of gas metal arc welding. Then the last one we'll talk about in this first pass anyways is submerged arc welding. And in this case, the electrode is again a wire, and it feeds through the welding nozzle. And the fluxing agent in this case is a powder, and the weld is actually submerged in the welding powder, and so that's where the word submerged arc welding comes from. So you can see here, this is the finer flux that goes right over the weld metal. This is the coarser flux, more granular, and then the weld electrode is actually feeding down through here, and down in this case underneath that pile of granular flux is where the arc is struck. Now there's often another tube coming back here behind this process that actually sucks up or vacuums up the flux powder that isn't used. So this process is limited. It's usually an automated process, not usually done by hand. So submerged arc welding is usually done automatically using some type of a robot or some type of a crawler type of mechanism. And this is what that might look like. So you would set this on top of two plates that were being joined together, and then you would program in the feed rate so that you could control how fast these wheels go. You can control how fast the electrode is fed through the nozzle. You can control how much flux is deposited and that sort of thing. It's really not practical to do submerged arc welding in a manual process. Okay, there are other examples of code-approved welding processes. You have gas metal arc welding using the short circuit method, and frankly, I don't know too much about that. You can have gas tungsten arc welding, and I think this is also referred to as TIG welding, but again, I'm not too familiar with that. And then you have electro-slag welding and electro-gas welding as well. Now, qualification is required for these processes. These aren't pre-qualified like the other four processes were. Now, I won't speak too much about these processes except for electro-slag welding. Electro-slag welding has some applications in structural engineering, probably more for bridge engineering than buildings, but if you're going to fabricate large girders or join large plates together, then electro-slag welding has some benefits to it. Basically, what you do is you take your two plates together in the form of a butt joint, and you put a dam, and that's illustrated here. This is the water-cooled jacket, they call it. It's copper, and it has cold water flowing through there, and it basically forms a dam on the edge. And you can see there's one on the front side here and another one on the back side here. And you basically deposit this weld from the bottom to the top using these water-cooled jackets on the front and the back to keep the molten weld metal from spilling out of the opening. So this is what it looks like in practice. This was a demonstration for us. So the plates that we're welding together are rather small. If it were something that was going to be done in practice, then this plate would extend on here, probably on the order of 10 to 12 feet, depending on the girder that's being fabricated. And you would see it come out the backside as well. Since this was just a demonstration project for a research project that I was working on some years ago, the plates are relatively small. But you can see here are the water-cooled jackets, right? So these red hoses come in and they keep cold water flowing through that copper dam in order to keep the copper from melting. And then the weld metal is deposited down through here, and then flux is deposited on top of the molten weld pool there. And the individual running this process is using this highly refined method of using this wooden stick to push some of the fluxing agent into the opening while the weld is being made. All right, now there are different positions that are used for welding, and if we're looking at a fillet weld, then the four positions are shown here. So you have a flat position and a horizontal position. Both of those are similar, but they're not quite identical, right? The flat position puts the face of the weld horizontally, whereas the horizontal position puts one of the legs of the weld horizontal. Then you have a vertical position and an overhead position that are shown here. So in general, it's much easier to weld in the flat or the horizontal position than it is to weld vertically or overhead. If you're welding vertically, you typically work your way from the bottom of the weld up and you stack it that way. In the overhead position, it's challenging because you have a molten weld puddle, and gravity wants to let that drip down from the workpiece, and you have to be able to combat that by using the right welding process, the right current configuration, etc. And this slide shows the four welding positions associated with groove welds. So again, we have the flat and the horizontal positions, also have the vertical position and the overhead position. Now, one thing to keep in mind is that when you specify welds, if you're able to weld in the flat or the horizontal position, you can be about 4 times as productive as you can be welding in the vertical or the overhead position. So if you're on a job site and you specify an overhead weld, you should be cognizant of the fact that that's going to be a costly weld to place. It's not easy to do, it's challenging, so it's going to cost more, it's going to take more time to place that weld, and that weld might be more susceptible to imperfections than a weld that was placed using the flat or the horizontal positions. All right, I'll spend a few minutes here talking about electrodes, but I'm not going to go into too much detail, at least in this recording. So there are a number of different electrodes that are available, and the electrode designation differs for each of the different welding processes. So basically, as the engineer of record, what you're worried about is the first 2 numbers that appear after the E. So in this case, an E70 means that the electrode has a 70 KSI tensile strength. The third number indicates the position code. So position code 1 means that it's good for all positions. If you had a position code 2, that would mean that it was only good for flat or horizontal positions. And then the fourth number indicates some coating characteristics. In this case, a 6 indicates that it's a low hydrogen. And then you have the weld metal composition as the last number. So in this case, an E7016-A1 electrode would be a 70 KSI electrode suitable for all 4 welding positions with a low hydrogen coating characteristic. Now, I will say one thing about weld metals. The terms matching and undermatched weld metals mean something to us. So typically, when you look at a base metal, if you're dealing with, say, an A572 grade 50 weld metal or base metal, you would have a yield stress F sub Y equal to 50 KSI, and you would have an F sub U equal to 65 KSI. Now, if you were going to use a matching weld metal for that, then that would mean that you would want to have a weld metal that has a tensile strength that is greater than 65 KSI. So E70 or greater would be a matching weld metal. They don't make an E65, they make an E60, an E70, an E80. They just come in increments of 10 KSI. An undermatched weld metal in this case would be one that has a tensile strength that is less than the tensile strength of the base metal. So in this case, E60 or lower would be an undermatched weld metal. Typically, you want to use matching weld metal. So you want to have weld metal or an electrode with a tensile strength that's greater than the base metal, but there are some cases where you can use undermatched weld metal and it'll be just fine. Okay, so for submerged arc welding, we have A517 and A523 that deal with the fluxes and the electrodes, and those designations are covered here. I'm not going to get into this too much in too much detail at this point, but in this case, you might want to note that an F7, for example, gives the 70 KSI minimum for the electrode. Here's a gas metal arc welding. In this case, it would be ER80, and in that case, it's an 80 KSI electrode. And then finally, the designation for flux-cored arc welding. So an E7X would be a 70 KSI electrode in that case. Okay, it's important to store the electrodes properly, especially if you have an electrode with the flux that's exposed. So if you have just regular shielded metal arc welding electrodes, stick welds, welding rod, for example, if you leave those out in an unsealed container, then the flux tends to absorb moisture. And if that happens, then you might end up with impurities in the weld. So it's important to keep the electrodes sealed until you're going to use them, and then after you've opened a sealed container, make sure you store them properly so that they don't absorb moisture. Typically, you'll see an old refrigerator with a light bulb inside of it. The light bulb keeps it warm in there and keeps the humidity low inside, and that works pretty well for storing electrodes. So this slide and the next couple address the idea of preheat and interpass temperatures. So basically, you're using a process where you strike an arc to melt the weld metal and part of the base metal. And if you're welding relatively thin parts, then that works really well. But if you're welding thicker parts, then the base metal can act as a heat sink, and it can cause the molten weld metal to cool too quickly, solidify too quickly, and you can get cracking of that weld. So to combat that, what you do is you preheat the base metal using some type of a flame, or you heat it between passes that you place of your weld metal. So this table here gives examples of what the minimum preheat and interpass temperatures are based on the thickness of the base metal that's being joined. So if you were welding 2-inch thick plates together, for example, then before you place the first pass, you would have to make sure that the base metal is at least 225 degrees Fahrenheit, and you'd have to make sure that it maintains that temperature between passes as well. So there's a maximum of 550 degrees Fahrenheit for your preheat and interpass temperatures, and that's to deter grain growth. And typically welders will use temple sticks in order to determine what the temperature is. Temple sticks are basically temperature indicating crayons. So you can buy them with a certain sensitivity, and you touch this this crayon to the steel, and if it melts, then you know that it is above the temperature for which that crayon was rated. So if you had a 225 degree interpass temperature, you would buy a crayon that was associated for that, and then you could heat the steel with a flame until the crayon melted, and then you would know you would have at least 225 degrees Fahrenheit. All right, now depending on which process we use, there are maximum sizes for the root pass, the first pass of the weld metal that's placed, and maximum sizes for each of the subsequent passes, the fill passes. So if you're dealing with stick welding, shielded metal arc welding, for example, and you're working in the flat position, you can place a root pass that has a 3/8 of an inch size. If you're working in a horizontal position, then it's only 5/16. If you're working in an overhead position, then it's 5/16 as well. If you're placing a single pass fillet weld, then we have the same dimensions that are shown there. So the biggest weld you could place in a single pass would be a 3/8 weld. Okay, if you're dealing with flux cord or gas metal arc welding, then you have these as your maximum sizes. So in the flat or horizontal position, you have 3/8 or 5/16 for the root pass, or in a fillet weld, you would have a 1/2 inch or 3/8 of an inch for the maximum single pass fillet weld. And then finally, for shielded submerged arc welding, rather, you can only perform this in the flat and the horizontal position, and basically you can deposit as much weld metal as you want. This is an automated process, so you can program the weld machine so that it goes slowly and has a nice uniform process to it. So it's unlimited in size. Now, one thing to bear in mind, however, is that generally it's not the engineer of record that specifies the process that's going to be used for welding. It's typically the fabricator that does that. So when you're specifying a weld size as the engineer, you want to bear in mind that depending on which process the fabricator selects, they might make it might be a process that requires multiple passes where you had envisioned it to be a single pass weld. So because you as the engineer probably don't know which process is going to be used, what you should do is stick to around a 5/16 as a maximum weld size as much as possible, so that you know that regardless of which process is used by the fabricator, they could place that weld with a single pass. So that's important, because when you consider the size of a weld, if you double the weld size, it actually ends up costing 4 times as much, because for going from a 5/16 to a 5/8 inch weld, you end up with a quantity that is 4 times as much. But the strength only doubles, right? So the weight for a 5/16 weld is about 0.166 pounds per foot, and the weight for a 5/8 weld is 0.665 pounds per foot. So you've increased the weight by a factor of 4, but you've only increased the strength by a factor of 2. So it would be more economical for you as the engineer of record to specify a 5/16 weld that was twice as long than it would be to specify a 5/8 weld that's half as long. And this is a table out of the AISC manual that gives approximate number of passes based on the type of weld you're using, the angle of the bevel that's being employed, and the size of the weld that's being made. So, for example, if you're placing a half-inch fillet weld, you can expect it to require 4 passes. If you're placing a 1-inch single bevel groove weld with a 30-degree bevel, then you can expect it will take approximately 5 passes. All right, now I alluded to the idea of backing bars and runoff tabs earlier, and this is a sketch out of the AISC manual that illustrates those pretty well. So we have a single V weld shown on the left and a single U weld shown on the right. And basically you have backing bars and runoff tabs that are shown here. So what's going to happen is the weld operator is going to place these welds, and they're going to come in with a root pass and place that root pass either moving from left to right as I'm showing here or moving from right to left, but they're going to start or end off of the edge of the plate so that they can come in after the welds are placed and remove the runoff tabs and the backing bars and then grind that smooth. If they didn't have the runoff tabs and the backing bars, then they would have to start at the edge of the plate, and you would end up with a rounded weld at the edge that would probably be full of imperfections. So then they'll come in and they'll place another pass here, come in and place another pass here, and they'll just basically make multiple passes across that opening until they fill that groove with weld metal. Then they'll come back in and remove the backing bar, remove the runoff tabs, and then grind the edges of the plate smooth, grind the top of the plate smooth, probably flip the plate over, maybe make one more pass on the back side before grinding that smooth as well. And for a well-placed weld, oftentimes it's challenging to find the weld after it's made. Okay, so here are some examples of how thick the backing bar has to be based on the weld process that's used. So for shielded metal arc welding, for example, you need at least a 3/16 backing. For submerged arc welding, you need 3/8. Okay, let's shift our attention now to weld symbols. We could spend a lot of time on this, but I'm not going to. I just want to give you an introduction at this point. So this is a typical weld symbol shown here. You have an arrow line pointing to where the weld is going to be placed. You have a reference line that gives some indication of what type of weld it is going to be placed. And then the tail is where you put the notes, like the electrode strength. So on the reference line, anything that appears below the reference line applies to the arrow side of the workpiece, and anything above the reference line applies to the other side of the workpiece. So for example, consider these three T-joints that are shown here. In the upper left, you have a fillet weld. So that's shown, the fillet weld symbol is shown there, and since it's on the lower part of the reference line, that means that the weld is placed on the side of the workpiece that is closer to the arrow. If we look down here, you again have a fillet weld symbol, but since that's on the top side of the reference line, that means that the fillet weld is supposed to be placed on the other side of the workpiece. So that means place the fillet weld down here instead of on the top. And then finally over here you can see there are 2 fillet weld symbols, one on the top and one on the bottom of the reference line. So that means place a fillet weld on both sides of the workpiece, both on the top and on the bottom. And then in each of those 3 cases, you can see that we're specifying an E70 electrode, which means that the electrode has a tensile strength of 70 KSI. Okay, here's a couple other examples. So this is a back-to-back T-joint, and you can see how 2 fillet welds will be placed on the top. They would be placed adjacent to the right side of the vertical piece. And on the bottom, you have 2 arrows coming out of that one weld symbol. So you place both of the fillet welds on the arrow side. So the reference comes below the reference line. So that means on the arrow side. So that means place it right here. And here's another arrow. So that means place it right there. Okay, now the numbers that are associated with the reference line indicate the size of the weld and the length of the weld. Okay, regardless of whether the reference is pointing from right to left, as is shown in the top, or from left to right at the bottom, the size is always the number to the left of the weld symbol, and the length is always the number to the right of the weld symbol. The vertical line of the fillet weld symbol is always on the left side, regardless of which way the weld symbol points. Okay, so this is a typical fillet weld. And what you'll learn in a different presentation is that the failure plane of the weld is through the throat, and that's illustrated here. So but when we specify the size of a weld, we don't specify the throat dimension, we specify the leg size instead. So we always specify W. We don't specify the throat dimension or the T dimension directly. So this would be the throat T, but bear in mind we're specifying W and not T. Okay, so this is an example of a fillet weld that would be placed on the near side of that T-joint. The fillet weld would have a leg size of 3/8 of an inch, and it would have a length of 12 inches. And it would look like that in 3 dimensions, though with that shaded black like it is, it's kind of hard to see. This is actually, you know, a triangular shaped weld, fillet weld, so that has a length that's 12 inches. And the leg size here is 3/8. Okay, here's an example of a fillet weld. So 3/8 is the leg size, and then there's 2-4. What that means is that there would be intermittent welds that are 2 inches long, spaced at 4 inches. So you would see that type of a stitch welding or intermittent weld placed, and it would only be placed on one side. It wouldn't be placed on both sides. In fact, since the weld symbol is above the line, the weld would be placed on the far side. Okay, you could place the weld symbol on both the top and the bottom of the reference line. Then you would get stitch welds on both sides. And oftentimes you'd want them arranged adjacent to each other like we're showing on the top, but maybe you want them staggered like we're showing on the bottom. And in that case, you just stagger the 2 fillet weld symbols like that, and then you get staggered stitch welds. Okay, now some other symbols you see quite often are a field weld with a little flag on it. That means that's welding that's anticipated to be done on the job site itself, not in the fabrication shop. And you also see this little circle at the joint of the arrow line and the reference line, and that generally means place a weld all around whatever it is that's going to be welded. So here's an example of an all-around weld symbol. So this is a column framing into a base plate, and this is a fillet weld that's being called out with the circle there. It just says weld all around the column, and so you would end up with a weld that looks like that. You have to be careful though. Some engineers will use the weld all around symbol a little bit too much, and you end up causing some problems in some cases if you don't use that judiciously. And then if you go to Chapter 8 of the AISC manual, you can see a more exhaustive table of weld symbols. So we have plug or slot welds, fillet welds, square welds, bevels, U, J, flare V, etc., etc., etc. So this is all available for you guys to peruse. And then further down in that table, it gives even more details of the arrow line, the reference line, and the tail of the weld symbols. All right, now this is taken out of Weld Symbols on Drawings by Gregory and Armstrong. And this provides a nice 3-dimensional view of what these different types of groove welds will look like. So I included that here for your reference as well. Our next topic is going to be that of pre-qualified joints, pre-qualified welded joints specifically. All welded joints must be pre-qualified, or they must be tested to prove that they're going to perform adequately. Now, an exception to this is fillet welded joints. All fillet welded joints are automatically pre-qualified. Basically, there's a series of pre-qualified joint details that are included in AWS D1.1, and there's a subset of those pre-qualified joints that are also included in Chapter 8 of the AISC manual. For these joints, you must have a written weld procedure specification for every weld, and the contractor is responsible for developing that. So this is an example of how you would specify, as the engineer of record, a groove weld between, say, a beam flange and a column flange. So this would be a T-joint, and it represents a single bevel weld with backing. So you have This guy right here indicates that it's a single bevel weld. This guy right here says use backing. And rather than just putting the electrode size in the tail, they've specified TC-U4A. And what that is a designation that references a pre-qualified joint that can be used in that application. And then I've shown here in orange the backing bar that might be placed. So in these pre-qualified joint designations, you have letters that specify the joint type. So a B would be a butt joint, a BC would be a butt or a corner, or in our case we had a TC, which represents either a T joint or a corner joint. You have the thickness or the penetration, so you have a P for a partial joint penetration weld, or an L for a limited thickness complete joint penetration weld, or a U for an unlimited thickness complete joint penetration weld. And then you have the welding process that's also specified. So if there's nothing there, if it's blank, it means shielded metal arc welding. If it's an S, it means submerged, G for gas, and F for flux core. Okay, the number represents the weld type that it's qualified for. So a 4 would mean a single bevel weld, a 7 would mean a double U, and then you have the welding positions, flat, horizontal, vertical, or overhead. And then, as I mentioned a couple of slides ago, all fillet welds are automatically pre-qualified. So if we look at that designation, the TC-U4A, it's specified for a T or a corner joint with an unlimited thickness for a complete joint penetration weld. The 4 indicates that it's a single bevel weld, and then the A is a sub-identifier. So there might be several welds that qualify for a T or a corner with unlimited thickness and excuse me, a single bevel, and this is the first one, sub-identifier A. Since the process isn't specified, that means it's adequate for shielded metal arc welding. So if you go to page 8-44 of your AISC manual, you'll actually see this pre-qualified joint spelled out. And they have different processes that are called out here. So a TC-U4A without the identifier is called out right here, and that qualifies for shielded metal arc welding or stick welding. So if you wanted to use gas metal or flux core arc welding, then instead what you would specify is TC-U4A-GF, or if you wanted to use submerged arc welding, then you would specify -S. And here you can see the thicknesses of the parts, T1 and T2. They're both unlimited in this case. If you're using stick welding, then you need a root opening of 1/4 of an inch with a groove angle of 45 degrees, or you need a root opening, of 3/8 of an inch with an angle of 30 degrees. And then you can see which welding positions are appropriate in those cases. All right, now a welder, the person or the contractor or the fabricator, whoever's making the weld, needs to have a procedure in place for doing that weld. Those are called Weld Procedure Specifications, or WPSs. And it's basically a recipe for placing a weld that is going to have a high quality and is going to perform the way that it's supposed to. So what's included in this is the type of base metal that's applicable, the thickness of the base metal that it works with, the type of joint, the type of weld, the position that is going to be used, the size of the weld, the root pass thickness, the fill pass thickness, the electrode class and size, what type of flux or shielding gas is being used, what is the flow rate of the shielding gas, what is the preheat and interpass temperatures, what type of voltage and polarity are you using for the weld machine, what type of amperage, travel speed, etc., etc. So basically, if a qualified welder looks at a weld procedure specification, they should be able to replicate that weld and place a high quality weld that is expected to perform the way we would expect it to. Now, to ensure that a weld procedure specification gives the results that we want, we do procedure qualification record testing, or PQR testing. Basically, what this means is you take two pieces of steel and you weld them together. All right, so this is a piece of base metal here, a piece of base metal here, and you form in this case, a single V weld prep, and then you fill this with weld metal like that. And then you come in after the fact and you remove a circular coupon, and it looks like a dog bone like this, and you take that to a test machine and you pull it until it breaks, and you make sure that you get the strength out of that you want. You also cut a couple of side bend specimens, one here at the top and another one here at the bottom. And those side bend specimens, and this shows the weld prep, where this is the single V, and you can see where the side bend specimens are going to be cut out here, and here's where that dog bone coupon would be cut out there. And I'm just wasting time trying to draw that. There, that doesn't look terrible. So those side bend specimens are then taken to a test machine, and they're bent sideways to see if you can develop any cracking in the weld. So here's an example of bending of a weld. This one's a little bit different. It looks like this one is a double V weld, but it's hard to see. But you can see the edges of the weld right there. So they're basically putting that into a test machine and bending it to see if any cracks develop in that weld, to see if the weld metal is any less strong than the base metal is. Okay, all fillet welds are pre-qualified by default, but if you have to test a fillet weld, then there's a procedure that's in place for that as well. And basically you make a mock-up of a specimen that's 12 inches long using 6 inches plates, and you place the weld and then cut it into pieces, and then you basically do some non-destructive testing on that to make sure that the weld is a high-quality weld. Okay, now in addition to qualifying weld procedures, you also have to qualify the welder. So the person that's actually running the welding machine and placing the weld has to be qualified, and they have to be qualified for each process that they're using, for each electrode designation, for each weld position, whether they're using backing bars or not, and they have to be qualified for certain thicknesses of the base metal as well. Okay, in addition, you also have welders versus weld operators. A weld operator is somebody that programs an automatic weld machine. It's like a submerged arc weld robot, for example. That would be a weld operator. A welder is somebody who actually holds the electrodes in their hand and places the welds manually. And then there's a third classification as well. A tack welder is somebody who fits pieces together and just places a small tack weld to hold those pieces in place until a welder or weld operator can come along and place the finished weld. So typically when you place a tack weld, that tack weld is only temporary and it gets melted and becomes part of the final weld. So the qualification of a tack welder is usually not as rigid as it is for a welder or a weld operator.